Of course, there are many other authors as well, but I only know these two persons because I've read many articles from them. And so this article, vertex sparsifiers, new results from old techniques. And so we construct 3 graphs. The first one, constructing a flow sparsifier edge that maintains congestion up to. So in this article, they work on 3 different things, but there are 3 different cases, let's say. Maintain congestion up to a factor of or log k over log k. So this sparsifier, this flow sparsifier, maintains the congestion until up to this factor. The second case that they talk in their article is a convex combination of trees. Convex combination over terminals that maintains congestion, now better, order of log k. And for planar graph, which is just special instance class, a convex combination of planar graphs that maintains up to a constant factor. And the novelty is just a new algorithm for zero extension problem. So let's talk about 2008 article of Reiki, which is highly cited, and it is optimal hierarchical decomposition for congestion minimization in networks. And they get a loss of log n using tree-based flow sparsifier, convex combination of trees. And this is the factor by which the congestion in G and H differs. And the Moitra loss got a better result, log k over log k. Because they didn't use a tree and they used an advanced version of Cqr invented by Talvar and those people. Now let's unify these using just the Reiki algorithm. And of course, in 2009, Anderson and Feige, they wrote an article, Interchanging Distance and Capacity in Probabilistic Mappings. It means that it is distance preserving and capacity preserving mapping. So the work of Rabbani is that the zero extension result, it gives order of log k over log k for flow sparsifier. So many people at the same time come up with this interesting factor. Of course, we can use zero extension with trees as well, because, the Talvar article, A Tight Bound on Approximating Arbitrary Metrics by Tree Metrics in 2003 is the way to go. And Anupam Gupta in 2010 they used improved approximation algorithm for requirement cut, and there are three embedding algorithm. Is there exists a randomized polynomial time algorithm that takes input graph G with terminals K and outputs edge-weighted two hierarchically separated trees with internal nodes. And then they said that it satisfies f of x and f of y. It should be in tree metric, it should be greater than in G metric, in just simple metric in G, for any x and y in K in terminals with probability 1. And also it should satisfy the expectation over all trees, because it's a randomized algorithm, of the distances between f of x and f of y is less than O log k d of x and y. And also for each non-terminal, v in v is not in k, either there exists a terminal sharing the leaf node with it, or another descendant of f of v parent in tree T that contains a terminal. So let's simplify that. Our motivation is that we want to preserve distances. We want to go from preserving distances to preserving capacities. So recall that a capacitated graph is a flow sparsifier with quality rho greater than 1, and any feasible k-flow in G can be feasibly routed in H. And any feasible k-flow in H can be routed. So let me show the final results. Any feasible k-flow in G can be routed in H directly. But the opposite one, any feasible k-flow in H, you have to pay, can be routed in G with congestion rho. And so interchanging distance and capacity is that we have some complex graph G. For example, this is G. This is a low distortion metric embedding, for example. And the original metric space is like this, U and V. It's a long story, so I just want to talk about something that can show you graphically. So let's start by Cqr algorithm is very important. So let's start by this article. In July 7, in 2000, Cqr Kalinski and Howard Karloff and Yuval Rabbani in 2000, They invented a very interesting rounding algorithm. So the extension player wants to minimize CUV, D of FU and FV and we define f of u to be I, we define f of I to be I if I is in terminal, and this is such that delta u and I is 0. So when we say metric relaxation of this zero extension problem, we mean that we can just minimize C of u and v, delta of u and v, and here, so any solution for the zero extension problem f is a direct solution for this extension problem. So for this let's say metric relaxation. So this is metric relaxation, and here the problem becomes delta of u and I is delta v and j, and then delta u and v is delta I and j, I mean d of I and j. So any solution for f leads to, you can solve it this. So you can go from this to the other one. And the multi-way cut, is just minimizing over all f, all zero extensions of C, U, and V. So we don't write any D here. So if it is simplified, then multi-way cut you can minimize it like this. So in other words, we find a set of edges of minimum total weight whose removal disconnects all terminal pairs. In other words, we want to minimize over all f, C of u and v, d of f of u and f of v. So zero extension is a natural generalization of multi-way cut. Instead of d being a uniform metric, d is an arbitrary semi-metric on the terminals. And it's interesting that metric labeling is a natural generalization of zero extension, because you want to minimize the assignment cost. Let's say it is a of u and f of u plus c of u and v, d of f and u and f of v, where a is t is terminal labels and it goes through R. So the LP relaxation of that. So let's get back to the original problem. The LP relaxation is the minimum of C of U and V, delta of U and V. So you have solved your problem and you get some fractional things and you want to round it. And delta INJ is just D of INJ if you just concentrate on the terminals. So the rounding procedure, the popular Cqr algorithm. So we have solved. So basically, we have solved our linear programming problems. So we should round it. Because, for example, you have solved it, and some D's between two vertices are, for example, 0.234, and another pair, the distance between them is 156, and then you should round them. There are many ways to round them. One of the best paradigms is randomized rounding. And the popular Cqr algorithm is just an example of randomized rounding. You can invent your own randomized rounding and enjoy that. And this is a probabilistic approach to rounding. So what is Cqr rounding? So the Cqr algorithm is like this. The algorithm is like this. We set f of t to t for all terminals t, and we pick a random permutation of the terminals. For example, first sigma 1, then sigma 2, then sigma k. For example, there is an order between them. First I pick this, then I picked, finally I pick sigma k. And we pick alpha uniformly as random between 1 and 2, and for any terminal, for example 1 to k terminals, for all unassigned terminals, because some of them are assigned in the previous steps. So what we are left is unassigned terminals U, such that the delta U and the distance, that fractional distance between U and sigma j, if it is less than alpha AU, then assign U to f sigma j. In other words, f of U is now sigma j. So what does it mean? It means that, for example, you have a U, you have V, and you have some terminals, for example, T1, T2, T3. But because we do this permutation in this algorithm, so they are not, they are permuted. So here we have T3, we have T4, we have T1, up to all of them. So if T3 cannot be a good match, so what if, for example, T1 is here. T1 is here, and the distance between U and T1, so let me clean this, T1. So if we start with T3, because T3 is the first, for example, here T3 is has a priority over T4, T1, and then T2, for example. First, we say that T3